So, introduction to communication systems. First, we'll get introduced with chronologically how things have developed. Starting with Maxwell's equations in 1864, the four famous Maxwell's equations, which actually predicted the propagation of electromagnetic wave and henceforth the advent of radio wave technology. We studied in electromagnetic course. Uh, in 1878, telephony, as developed by Alexander Graham Bell, henceforth Morse codes, compression of data, all the concepts were developed post these era. In 1887 to 97, first experimental verification of Maxwell's equations by Henry Hertz, uh, along with of J.C. Bose from India, Marconi from Italy, Popov from Russia. They demonstrated wireless telegraphy. Oliver Lodge demonstrated wireless communication in some form. 1905 to 1915, the Lee De Forest invents triode, a precursor to transistor. G.A. Campbell invents filters in Bell Labs, and AM radio broadcasting was invented. AM radio broadcasting started. Filters helped in equalization, triodes helped in amplification. 1918, a very important concept known as super heterodyne radio receiver. This was developed by E.H. Armstrong. Armstrong is a very key figure in context of wireless communication, in context of communication circuits. Uh, a super heterodyne radio receiver we still use in modern day technology. In 1920 to 28, we have a series of theoretical papers, Theory of Signal Transmission by Carson, Harry Nyquist, Concept of Noise and its Effect in Signal Transmission by Johnson, Primitive Form of Channel Capacity and Bandwidth by Hartley. All Bell Lab guys. In fact, Carson analyzed the spectrum of frequency modulated signal. However, Carson kind of did not uh, correctly predict the performance of FM. In 1936, FM radio was invented again by Armstrong, same person, E.H. Armstrong, and he demonstrated to the technical community members the strength of FM over AM. In 1937, A. Reeves conceived the concept of pulse code modulation, and henceforth came the digital era. PCM, pulse code modulation, we'll study a little bit of it, which actually led us to the we actually led us to something known as digital communication, which we'll study next semester. 1944 to 47, we have classical papers by Rice on statistical communication theory, on theory of noise, random process, along with Wiener, Kolmogorov from Russia, Kotelnikov from Russia. They developed optimum signal detection in the presence of noise. We have Wiener, Kolmogorov filter, Wiener's equation. We'll study a little bit of that when we study random process. So the concept of performance of a communication system in the presence of noise was developed by around this era. 1948 to 450, this is known as one of the golden era of communication. Claude Shannon, he developed information theory and coding. Classical papers developed the whole concept of information theory and henceforth coding theory. Okay, 1955, J.R. Pierce proposes satellite communication systems. Satellite communication systems helped us in communicating over a larger distance and the advent of modern day technology. 62 to 66, high-speed digital communication was developed. Viterbi and others contributed a lot in this area. 1972, Motorola developed cellular telephone. That is the first cellular telephone developed by Motorola. 1979, 1G was launched by NTT Japan. Around 1980-81, it was launched in USA. 1990, the era of communication shifted to 2G digital communication systems. Wi-Fi for WLAN, wireless LAN standards were developed. 1998, digital television service replaced analog television service. This is again a key development. 2000, we have 3G cell phone systems providing higher data rate. WiMAX system came to picture. There were various standards which evolved. For example, 802.11, various A, B, C, D, all addendum standards, and um, OFDM was primarily a choice of modulation, orthogonal frequency division multiplexing. The concept, the technology of ultra wideband technology was developed around 2002. In 2010, the standards moved towards the cell phone. Um, Standard moves towards 4G with enhanced data rate. 2020, we expected 5G cell phone service to launch globally, and 5G, the fifth generation cell phone, uses modern technology, something known as MIMO systems, multiple input multiple output systems. In MIMO, what we do is we use multiple transmitting antenna on the transmitter side, and we use multiple receiving antenna on the receiver side, and henceforth we can achieve higher data rate, we can achieve better, or in better diversity to tackle something known as channel fading. Okay, so this is broadly where we stand today. The next page, we have discussed a little bit on various kinds of communication frequency bands and their application. However, still I included it here to understand something known as transmission media and propagation modes. So in the frequency of 1 kilohertz, we have typically telephone, telegraph, or in the lower frequency range like 10 kilohertz to 100 kilohertz, we have aeronautical, submarine cable, navigation, transoceanic radio. The this is known as very low frequency to low frequency band. Uh, our propagation, our transmission media that we use in this propagation mode, in this propagation band, is cable, just standard wire pairs, twisted pairs, which you see in your laboratory. The propagation over this frequency range is over ground wave radio. A slightly higher frequency, around a megahertz or so, we have amplitude modulated broadcasting. We have several kinds of radio, commercial or business purpose radio, amateur radio, civil defense. Around 30 megahertz or so, we have we have certain kind of mobile radio, disaster management radio, 100 megahertz VHF television, and frequency modulated systems. Uh, this band is known as medium frequency, high frequency, and very high frequency, in short form HF to VHF. The propagation systems which you use are known as coaxial cable. Coaxial cable, you have one center conductor, and outside you have an external conductor which is typically grounded. In between the central conductor and the external conductor, you have some dielectric. The premium mode of communication is basically skywave radio or sometimes line of sight. As you go to even higher frequencies, for example, ultra high frequency, which is around couple of megahertz, 300 megahertz or so, to around a range of 1 gigahertz or even more, 5 gigahertz, you have applications like broadband, personal cell phone service, wireless communication services, cellular, pagers, narrowband PCS, GPS signals, and so on and so forth. So even high frequencies, SHF, super high frequency, we have applications of above around 10 gigahertz or even more. We have Earth satellite, radar, microwave relay, satellite navigation, and the typically used communication transmission media is waveguides. We did not study in electromagnetic theory this concept, but waveguides offer much less loss compared to coaxial cable at this high frequency. Waveguides are hollow metal cylinders, or they may be printed over a dielectric, which allows wave propagation through various kinds of modes, TETM modes. Even higher frequency range, you have optical fibers, and these are used for terahertz communication. Now, what are the elements of a communication system? Okay, the elements of a communication system, we have a transmitter, transmitting channel, and a receiver. The transmitter receives signal from the source. The activity performed by transmitter is modulation and coding. The signal is transmitted from the transmitter, passes through the channel. Channel introduces noise, interference, distortion. These are present in any communication channel. The signal is received by the receiver. In the receiver, first the signal received is very weak in strength, so appropriate amplification and filtering of the signal is performed to reduce noise and interference. Then just the inverse processing is done as in transmitter. For example, instead of modulation, we do demodulation. Coding is done in transmitter. The coded signal is decoded in the receiver, and finally we have the output signal. So the channel distortion. What is distortion? The waveform perturbation caused due to the imperfect response of the system. A signal waveform that passes through a channel. Imperfect response means the channel may have different amplitude and phase response over the frequency band, and henceforth the waveform gets distorted. So this is typically corrected by something known as channel equalizer in the receiver end. So channel equalizer can be implemented in analog mode, or in more, if possible, you can discretize the signal, go to digital domain, and then you have the flexibility of implementing something known as adaptive equalizer, where you can adapt the various taps of the equalizer depending on the channel scenario. Channel changes, you can correspondingly adapt the equalizer. Interference. What is interference? Interference is contamination by extraneous signals from other sources. So other human or non-human machine or atmospheric sources can have signal in the frequency band of interest. So these are known as extraneous signal, and they can be removed in the receiver by something known as filtering. Noise. This is a very important thing in communication system. Without noise, actually the job of a communication engineer almost reduces to very triviality. It is due to the presence of noise that the work of a communication engineer is so much challenging. So noise is any random and unpredictable signals produced by natural process. So typically modeled as a stochastic process. That's why it is very important for us to understand or to know that random process and its various mathematical nitty-gritties. It cannot be completely removed. Noise cannot be completely removed from the received signal. Maybe you can filter out and throw away certain portion of the noise in the band where the signal does not, where the signal of interest does not exist. But it cannot be removed from the band where the signal and noise coexist. And this constitutes one of the fundamental system limitations. Noise is the most important fundamental system limitation. In fact, there are two fundamental limitations of information transmission. One is the bandwidth. The spectrum is very precious. All of us share the same spectrum. And the second thing is noise. So, 1948, the landmark paper by Claude Shannon, father of modern day communication theory, who proposed, mathematically derived in fact, rate of information transmission cannot exceed channel capacity. Channel capacity is a concept which we'll discuss much later in the course a little bit. So what we have is the channel capacity is given by B log base 2 1 plus S by N. So B is my bandwidth of my signal, log base 2 1 plus S by N. S by N is known as signal to noise power ratio. So the channel capacity is calculated based on this with the assumption that the noise is Gaussian. The rate of information transmission cannot exceed this channel capacity. So we have to actually work below this what is provided by the Shannon's limit for error-free transmission of information. Okay, now let's see how does noise interference distortion look. So let's see this picture. So we are sending pulses 1 1 0 1 0 0 1. For 1 we have certain voltage square wave, and for 0 we have 0 volts. So let's say this is our signal of interest. Now you see, when we transform, when we through the transmitter, when the signal is transmitted, effects of distortion. Effect of distortion, you see that the signal has been uh, the sharpness of the signal is lost. It has become it has spread over to the next symbol. This one has spread over to the next symbol, and this is known as inter-symbol interference. So the symbol from this portion 1 has spread over to this 0. The signal from 0, which was supposed to be 0 up till here, has started to move to 1. So if that is very rapid change, if the symbol width is very small, and there is a very rapid change of ones and zeros, then these things are smeared, they are not so distinct. So effect of distortion is basically smearing the signals and henceforth cause something known as inter-symbol interference. So appropriately pulses needs to be designed, appropriately equalizers needs to be designed such that one can take care of this kind of distortion. Effect of figure C, effect of interference. See, interference is extraneous signal which has been superimposed on the actual signal. So this signal is generated from some other source, and henceforth if you know the appropriate frequency, you can design a notch filter and you can cancel this interference. Effect of noise. You see, unlike an interference which has certain frequency pattern, noise is relatively random. And if the noise margin is such that the ones reaches zeros, zeros reaches ones, if the noise excuse me, if the noise level is high or signal to noise level is poor, ratio is poor, then it's very difficult to detect the presence of 1 or 0, and henceforth this may cause some error. Okay, so the transmitter does two very important tasks to handle, for efficient transmission, to handle the effects of this channel, the unwanted effects of this channel. One is modulation, one is coding. We'll just briefly see what are them. First we'll discuss about modulation. Modulation is a signal processing operation. Coding is a symbol processing operation. So in modulation, the signal, transmitted signal itself is processed. Information is contained typically in baseband signals and are not suitable for direct transmission. Why it's not suitable? Because the dimension of the transmitting antennas or transmitting frequency where you want to transmit, such that you can share various kinds of information and transmit together. So these needs to be very practical. These signals are henceforth modified to facilitate transmission, and this modification is known as modulation, which helps in shifting the signal spectra. So there can be a linear shift, just translation of the signal spectra, or there can be a non-linear shift, which is angle modulation or angular modulation, frequency and phase modulation. The baseband signal is used to modify some parameters of a high frequency carrier signal. So the baseband signal is used to modify some parameters. So baseband signal contains information. The parameters what we mean are the amplitude or and frequency or and phase of high frequency, the high frequency signal which is known as carrier signal. Over the carrier signal, the information is embedded over the carrier signal, and the carrier signal is transmitted through the antenna. At the receiver, the modulated signal must pass through a reverse process called demodulation. It removes the effect of the carrier signal and reconstructs back the baseband signal. So what does modulation help? Modulation helps in ease of radiation. At higher, typically, as we said, the dimension of the transmitting system is that means the antenna. The physical dimension should be at least quarter wavelength or so. It cannot be much less than let's say less than quarter wavelength or 1/8 of a wavelength would be a very poor radiator. So you want an efficient radiator. Henceforth, the antenna physical dimensions must be of that order, and if the frequency is not high, then the wavelength is large, and henceforth the dimensions are very big, which is impractical. So appropriate choice of frequency would lead us to smaller antennas. Physical dimensions of the antenna is small and very practical to implement. Simultaneous transmission of several signals. So frequency assignment and something known as frequency division multiplexing. So we can, so for example, your speech signal, mine speech signal all occupies the same band. Let's say 0 to 4 kilohertz. Now we want to transmit all our signals together. I cannot use that frequency of that frequency band to transmit. I have to translate it to some higher frequency. Let's say 10 megahertz, over which I can assign 4 megahertz to you, 4 kilohertz to you, 4 kilohertz to me, and to other people, and henceforth I can around that 10 megahertz carrier frequency. So this is known as frequency assignment. Along with this comes something known as frequency division multiplexing. So what we can do in frequency division multiplexing is we can simultaneously transmit our information or information from various sources using the same carrier frequency, and henceforth this is an efficient transmission scheme by modulating. No? So it provides a trade-off of SNR and bandwidth. Recall Shannon's very famous formula, which we just now studied, which is channel capacity is related to bandwidth times log 1 plus signal to noise ratio. So I can improve upon SNR, or I can improve upon the bandwidth to achieve the same channel capacity. I can trade off between SNR and bandwidth. I can improve upon SNR, reduce my bandwidth. I can do vice versa, increase bandwidth for the case where the noise is very high, and henceforth I can play around the process to reduce the effect of noise and interference. So modulation helps us in trading off with this SNR and bandwidth. And the very important reason why we do modulation is overcoming hardware limitations. By modulating at higher frequency, so one reduces the fractional bandwidth, the bandwidth B of a signal, and if we use the carrier frequency FC, so the fractional bandwidth is defined as B by FC. So by modulating at higher frequency, that means the bandwidth contains the information content, so I cannot change that. So more and more higher FC that we move, we have lesser fractional bandwidth. Lesser fractional bandwidth means my cost or my design process of my amplifiers, filters, antennas, they will be very easy, and they will be relatively low cost. Okay. Now the second important thing what a transmitter does is known as coding. Coding is a symbol processing operation. Instead of signal, it operates on the symbol. Henceforth, the moment we use a symbol means ones and zeros. If it is a binary symbol, it is very suitable for digital systems. So, like not much for an analog system. So analog system can be converted to digital system using pulse coded scheme, PCM. So in coding, we have two broader perspectives of coding. One is known as source coding. The second is known as channel coding. What do we do in source coding? Source coding takes advantage of the statistical knowledge of source signal to enable efficient encoding. So the source signal, if there is larger occurrence of certain symbols, you assign lesser amount of bits for it. The occurrence of a symbol which is rare, you assign more amount of bits for it. So effectively, you basically reduce the overall bit rate. It reduces redundancy to achieve transmission efficiency. Channel coding actually introduces controlled redundancy to improve reliability in noisy channel. It takes care. So source coding is related to the signal, source signal, and the knowledge of the signal. Channel coding is related to the knowledge of the channel. Channel is noisy. We can take care of this noisy channel or reduce the effect of this noisy channel by introducing redundancy. That means maybe we add one more extra bit and say that, okay, you check that a number of ones are parity bit, number of ones are odd, or number of ones are even. If it is not, then you understand that there's an error and you acknowledge that in the to the transmitter. So it improves reliability, and henceforth source coding and channel coding combined together. So this reduces redundancy, this introduces redundancy, combined together provides a very efficient methodology of transmitting signal. So this is huge beneficial for digital communication systems. That's why we move. That is one of the primary reason. If possible, we try to use a digital communication techniques. Fine. So I'll stop over here. In the next lecture, we will discuss about signal distortion in transmission while transmission. We'll study about various kinds of distortion, linear, non-linear, and so on and so forth. Thank you.